Robert W. Floyd's 1968 paper, Assigning Meanings to Programs, stands as a crucial milestone in the development of formal methods for software verification. This essay undertakes a comprehensive examination of the seminal work, meticulously dissecting its claims, arguments, and underlying methodology. The analysis will proceed section by section, evaluating the paper's assertions and illuminating their significance within the context of programming language theory and software engineering. Section 1, Introduction, and the imperative of verification. Floyd's paper initiates a paradigm shift in how programmers, and by extension, computer scientists, conceive of program correctness. It posits that meaning can be systematically assigned to programs, enabling rigorous proof of their adherence to specified behaviors. The introduction argues, implicitly, for a move beyond ad hoc testing as the primary means of assurance, advocating instead for a mathematical foundation upon which program reliability can be erected. It is more than simply suggesting correctness, but outlining how correctness can be achieved through a specific technique, a monumental contribution. Floyd's initial framing implicitly criticizes the then dominant approach to program validation, which relied heavily on empirical testing. Testing, while valuable, can only demonstrate the presence of errors, not their absence. Floyd's approach aims to demonstrate the absence of errors for all possible inputs, transitioning away from sample cases. The paper's opening remarks thus signal a clear intent to furnish programmers with tools and methods capable of elevating program correctness from an aspiration to a provable certainty. Section 2, the concept of interpretation and state variables. Floyd then delves into the concept of interpretation, laying the groundwork for his axiomatic approach. He introduces the notion of a machine state, encompassing all relevant variables that influence program execution. The paper presents this state as an abstraction, comprising assignment of values to program variables. The meaning of a statement, within Floyd's framework, is defined by its effect on this state. This is a key idea. Statements are not merely instructions, but transformations. More specifically, the meaning is a relation between the state before execution of the statement and the state after execution. This relation is implicitly a mathematical function mapping from one state to another. The section presents a novel perspective on computational semantics, moving beyond operational descriptions to a more declarative understanding. The introduction of state variables allows for the formalization of program behavior in terms of pre- and post-conditions, paving the way for subsequent verification techniques. The notion of global state is both powerful and creates complexities addressed in later research expanding on Floyd's work. Section 3, Assignment Statements and the Substitution Rule. The paper gives specific attention to assignment statements, detailing how these statements alter program state. Floyd enunciates a substitution rule, which states that the postcondition following an assignment must be obtained by substituting the new value of the assigned variable into the precondition. Consider an assignment statement such as variable x assigned the value of expression y. Floyd's substitution rule indicates that if a postcondition, call it Q, must hold after the assignment, then the precondition needed before the assignment is found by replacing every occurrence of variable x in Q with expression y. This principle, while seemingly straightforward, represents a significant leap in formalizing program semantics. It provides a precise means of reasoning about the effect of assignment statements and forms the bedrock of axiomatic verification. Furthermore, the explicit articulation of the substitution rule offers an algorithmic approach to deriving preconditions from desired postconditions, providing a powerful tool for program verification. The elegant simplicity of the substitution rule belies its profound implications for subsequent developments in formal methods, illustrating a fundamental component of program semantics in a mathematically rigorous. Section 4, Conditional Statements and Branching Logic. Floyd continues his exposition with an analysis of conditional statements, often embodied in if-then-else constructs. He argues, verification of a conditional statement necessitates demonstrating the correctness of both branches, the then branch under the condition of the statement being true, and the else branch under the condition of the if statement being false. This approach embodies a case-based reasoning strategy. To prove the correctness of the entire conditional statement, one must demonstrate that, assuming the precondition holds, either the then branch leads to the desired postcondition when the condition is true, or the else branch leads to the desired postcondition when the condition is false. The paper meticulously underscores the importance of covering all possible execution paths. This methodical approach to conditional statements elucidates the branching logic inherent in programs and provides a systematic method for verifying its correctness. It emphasizes exhaustiveness. All potential execution paths must be subject to formal scrutiny. Section 5. Iterative loops and the concept of invariance. Floyd's treatment of iterative loops constitutes a pivotal contribution, introducing the concept of loop invariance. A loop invariant is a condition that holds true before, during, and after each execution of the loop body. Finding a suitable loop invariant is essential for proving the correctness of a loop. The invariant serves as a stable assertion that captures the essence of the loop's behavior, allowing one to reason about its overall effect. The paper implicitly acknowledges the inherent difficulty in identifying appropriate loop invariants, suggesting that this process often requires significant ingenuity and understanding of the loop's purpose. Once a valid invariant is established, one must demonstrate that the loop terminates and that the invariant, combined with the termination condition, implies the desired postcondition. This section underlines the critical role of invariance in reasoning about repetitive processes, providing a vital instrument for program verification. The identification of invariants is frequently considered an art dependent on the programmers. Section 6. Flowcharts and visual representation. Floyd employs flowcharts as a visual aid to illustrate the flow of execution and the placement of assertions. These flowcharts represent a program's control flow, depicting the sequence of operations and the points at which conditions are evaluated. The use of flowcharts facilitates a graphical representation of pre- and post-conditions, making it easier to visualize the relationships between program states. Annotating flowcharts with assertions provides a clear and intuitive means of tracing the evolution of program state and verifying the correctness of individual steps. The integration of flowcharts into the verification process exemplifies a practical approach to program analysis, combining formal rigor with visual clarity. While modern verification techniques often rely on symbolic execution and automated theorem proving, Floyd's use of flowcharts highlights the value of visual representations in enhancing understanding and facilitating manual verification. Section 7. A simple example computing factorial. Floyd illustrates his methodology with a concrete example computing the factorial function. By applying his axiomatic approach, he systematically derives the pre- and post-conditions necessary to ensure the correctness of the factorial program. This example serves as a demonstration of the practical applicability of his theoretical framework. He meticulously details how the assignment statement rule, conditional statement analysis, and invariant maintenance work together to prove the program achieves the desired result. The careful execution of his methodology through a simple demonstration provides concrete evidence supporting his claims. The illustrative example of the factorial function, while elementary, serves as a compelling demonstration of the power and elegance of Floyd's axiomatic approach to program verification. He shows specifically how preconditions, assignment rules, conditional statements, invariants worked. Section 8. Further applications and complexity considerations. Floyd briefly alludes to the potential for applying his methodology to more complex programs, including those involving arrays and other data structures. He acknowledges that verification of such programs can be significantly more challenging, requiring more sophisticated techniques and careful consideration of aliasing and side effects. The paper also implicitly recognizes the need for automated tools to assist in the verification process. particularly for large and complex programs. Despite the inherent difficulties associated with verifying complex programs, Floyd remains optimistic about the potential for formal methods to improve software reliability. He suggests that continued research and development in this area will lead to more powerful and effective verification techniques. The paper serves as a call to action, urging researchers to tackle the challenges associated with scaling formal methods to real-world software systems. The call to action is implicitly based on the idea that the foundations and principles have been established at a basic level. Section 9 Logical Foundations and Completeness concerns. The text does not delve deeply into the specifics of the underlying logic used to express assertions and reason about program correctness. Rather, it assumes a degree of familiarity with predicate logic and first-order logic. A complete analysis of the paper demands consideration of the logical system's limitations. The expressiveness and completeness of the logic directly impact the ability to formulate and prove assertions about program behavior. Incompleteness, for instance, can mean that true assertions may exist that cannot be derived within the formal system. Furthermore, the decidability of the logic is crucial. If the logic is undecidable, then there exists no algorithm which can determine, in all cases, whether a given assertion is true or false. Floyd's framework inherits these potential limitations. Further research and refinements to the logical foundations of program verification are warranted. Section 10, Connection to Hoare Logic and Refinement. Floyd's work served as a direct precursor to, and greatly influenced the development of, Hoare logic, or built upon Floyd's ideas, formulating a more systematic and structured approach to program verification based on pre- and post-conditions and inference rules. Hoare logic formalized the notion of Hoare triples, written as PCQ, where P represents the precondition, C is the program code, and Q is the postcondition. This notation provides a concise and rigorous means of specifying and verifying program behavior. The relationship between Floyd's system and Hoare logic is one of evolution and refinement. Hoare's logic provides a more structured framework. Floyd's original contribution laid the groundwork for Hoare's more formalized and widely adopted approach to program verification. Subsequent work has explored the application of Hoare logic to a wider range of programming languages and paradigms. Section 11 Limitations regarding concurrency. Floyd's paper, being a foundational work from 1968, primarily addresses sequential programs lacking explicit treatment of concurrent or parallel programs. The introduction of concurrency introduces significant challenges to program verification due to the non-deterministic nature of thread interleaving and the potential for race conditions and deadlocks. Proving correctness in a concurrent setting requires extending the axiomatic approach to account for these additional complexities. The development of formal methods for concurrent program verification remains an active area of research, building upon the foundations laid by Floyd and Hoare, but incorporating techniques such as temporal logic and model checking. Floyd's focus on sequential programs reflects the state of computer science at the time, but it also highlights the need for further research to address the challenges of verifying concurrent and distributed systems. Section 12 Impact on program synthesis and compiler optimization. Floyd's focus on semantics has indirect but powerful implications for automated program synthesis and compiler optimization. His work on assigning meanings to programs provides a foundation for automatically generating code from formal specifications, or vice versa. If programs can be proven correct with respect to specific requirements, logic can be inverted to derive code from specifications. Also, the explicit representation of program semantics allows compilers to perform more aggressive optimizations while preserving program correctness. The analysis of program meaning enables compilers to identify and eliminate redundant computations, reorder instructions, and perform other transformations that improve performance without altering behavior. The connection between program verification and program synthesis continues to be an area of active research, as does the use of formal methods in compiler design and optimization. Section 13, addressing criticism. Regarding practicality, a recurring criticism of formal verification techniques, including those originating from Floyd's work, concerns their perceived lack of practicality for real-world software development. The argument goes that applying formal methods to large, complex software systems is too time-consuming and requires specialized expertise. However, advancements in automated theorem proving, model checking, and static analysis have made formal methods more accessible and practical. Tools and techniques are available to partially automate the verification process, reducing the burden on programmers. Moreover, the increasing cost of software failures and security vulnerabilities has heightened the need for more rigorous development practices, making formal methods more attractive in critical domains, such as aerospace and medical devices. Formal verification is increasingly considered a necessity. While challenges remain, the perception of formal methods as being impractical is gradually diminishing. Section 14. The subtle art of abstraction. Throughout his work, Floyd implicitly acknowledges the importance of abstraction in the verification process. He uses abstract concepts to represent program states, simplifies the semantics of programming languages, and ignores low-level implementation details. Deciding what to abstract away and what to retain is a critical aspect of successful program verification. Over-abstraction can lead to inaccurate or incomplete verification results, while under-abstraction can render the verification process intractable. The art of abstraction involves finding the right balance between simplicity and accuracy, capturing the essential aspects of program behavior while minimizing complexity. This section acknowledges the subjective element involved in the application of his method. Section 15, the relevance to modern formal methods. Floyd's seminal paper retains significant relevance to modern formal methods for software verification. Modern techniques, such as model checking, abstract interpretation, and symbolic execution, build upon the foundational principles established by Floyd. While these modern methods often employ more sophisticated algorithms and tools, they share the same fundamental goal to provide rigorous assurance of program correctness. The work provides a conceptual framework that remains applicable to a wide range of verification techniques and programming paradigms. The enduring relevance of Floyd's paper stems from its focus on the underlying semantics of programs, a concern that remains central to all formal verification efforts. The ideas presented find homes in current approaches. Section 16, on challenges with infinite state spaces. A significant challenge in program verification arises from the possibility of programs occupying infinite state spaces, programs with unbounded loops, recursive function calls, or dynamically allocated memory can exhibit infinitely many possible states, making it impossible to explicitly enumerate and analyze them all. Handling infinite state spaces requires techniques such as abstraction, approximation, and induction. Abstraction involves mapping the infinite state space to a finite one, allowing for tractable analysis. Approximation involves over-approximating or under-approximating the set of reachable states. Induction involves proving properties over infinite state spaces by establishing a base case and an inductive step. Floyd implicitly acknowledges this challenge, and modern approaches strive to provide practical solutions for programs with unbounded behavior. This represents an area of ongoing research. Section 17, the significance of domain-specific languages. Floyd's principles can be successfully applied to the design and verification of domain-specific languages (DLSLs). Domain-specific languages are programming languages tailored to a specific application domain, such as financial modeling, hardware description, or web development. By formally defining the semantics of a DSL, one can apply Floyd's axiomatic approach to verify the correctness of DSL programs. The use of formal methods in DSL design can lead to more reliable and maintainable systems, particularly in safety-critical domains. The connection is natural. A specific logic and type system is built for the domain. Section 18 extensions addressing data structures. While Floyd's initial examples focus on simple data types, such as integers, his methodology can be extended to handle more complex data structures, such as arrays, linked lists, and trees. Handling data structures requires careful consideration of aliasing, pointer arithmetic, and memory management. Techniques such as separation logic have been developed to address these complexities, providing a more precise and modular way of reasoning about programs and manipulate data structures. The incorporation of separation logic into formal verification tools has significantly increased their ability to handle real-world programs that rely heavily on data structures. The need for such work has grown since Floyd's original contribution. Section 19. The crucial role of human intuition. Despite advancements in automated verification tools, human intuition remains crucial in the verification process, identifying invariants, formulating assertions, and guiding the verification process often require deep understanding of the program's behavior and purpose. Automated tools can assist in the verification process, but they cannot replace human insight altogether. The interaction between human intuition and automated tools is essential for successful program verification. Effective use of formal methods requires a blend of technical expertise and creative problem-solving skills. This recognizes the limitations of full automation and the value of a human in the loop. Section 20. The enduring legacy and future directions. Floyd's work on assigning meanings to programs has had a profound and enduring impact on the field of computer science. His axiomatic approach to program verification laid the foundation for subsequent developments in formal methods, program semantics, and programming language theory. Modern techniques build upon the principles originally outlined by Floyd. Future research directions include the development of more automated and scalable verification tools, the application of formal methods to emerging programming paradigms, and the integration of formal methods into the software development lifecycle. The legacy of Floyd's paper extends far beyond its immediate impact, shaping the way we think about program correctness and inspiring generations of researchers and practitioners. The paper remains a relevant starting point for anyone interested in formal methods for software verification. The paper initiated a field. In conclusion, Floyd's 1968 paper is a landmark achievement. Its section by section articulation of an axiomatic approach provides a robust framework for assigning meaning to programs and verifying their correctness. While subsequent research has built upon and refined his ideas, the core principles remain foundational to the field. The work demonstrates the power of formal methods to enhance software reliability and provides a clear path toward building more trustworthy systems. Its enduring significance lies not merely in its historical context, but in its continuing influence on the theory and practice of computer science, and in the ongoing efforts to realize its vision of provably correct software